Next we will see standard form of second order system. So this is the block diagram of second order system. So R of S is the input, omega n squared divided by S into S plus 2 zeta, we are calling this one as zeta, into omega n, that is the function g of s. Okay, that is the gain of forward path, and we are considering unit feedback system, and it is a negative feedback system. So if you simplify this one, then we will get a standard form of transfer function, that is t of s is equal to, we can write y of s or output as c of s, that is c of s divided by r of s, or y of s divided by r of s, equal to omega n square divided by s square plus 2 zeta omega n into s plus omega n square. So after simplifying this one, you will get this form, that is we are calling this one as a standard form for second order systems. So here omega n is a system natural function, actually omega n is system natural function, and zeta is a system damping ratio. So in the next slide we will see what is the damping ratio and omega n. So some of the important parameters here. So the system damping ratio, that is zeta, and yeah, before going to this, I will tell you, see the second order system, how to identify second order system. So in the previous concept, I told that in the standard uh, equation, the denominator term, that is a into s to the power n, that a into s to the power n will give, that n value will give the order of the system. So till now we studied s to the power 1, that n is equal to 1, so first order system. Now if s in the denominator in this equation, omega n square divided by s square, so here n is equal to 2, so that's why it is called a second order system. So next we'll see different parameters. So system damping ratio, that is denoted by zeta. It is a dimensionless quantity describing the decay of oscillations during a transient response. So we know that there are output response contains transient response and steady state response. This transient response contains oscillations, and it is keep on decreasing. Oscillation will keep on decaying, and finally it will go to steady state. So there will not be any oscillation. So that part is called as steady state. So this zeta is a dimensionless quantity describing a decay of oscillations during a transient response. How much it is decreasing, in what amount it is decreasing, that oscillations, that will be given by the factor or value zeta. It is the ratio of actual damping to the critical damping of a system. It is the ratio of actual damping to critical damping of the system. The next one is omega n, that is a system natural frequency. It is the angular frequency at which system tends to oscillate in the absence of damping force. So omega n is the natural frequency. So in the absence of a damping force or damping ratio zeta, the system should oscillate. So that is omega n. And another factor parameter is omega d, that is system damping frequency. So that is denoted by omega d, that is angular frequency at which system tends to oscillate in the presence of damping force. In the presence of damping force, that is zeta, it tends to oscillate. So that is omega d. Omega d is given by omega n square root of 1 minus zeta square. In the derivation, we will come to know what is how to find out how we will get this omega d. That is omega n into square root of 1 minus zeta square. So next we'll see different type of responses of second order systems. So based on the value of zeta, there are different type of second order systems we can identify. That is, response of second order systems mainly depends upon the damping ratio zeta, For any test input, the response of a second order system can be studied in four cases depending on the damping effect created by value of zeta. So that is first one is if this zeta value is greater than 1, that is a dimensionless quantity. If zeta is greater than 1, it is called as overdamped system. If zeta is equal to 1, it is called as critically damped system. If that zeta is between 0 and 1, it is underdamped system. And if zeta is equal to 0, then it is called as undamped system, undamped second order system. And next one is damping and types of damping. So damping is an effect created in an oscillatory system that reduces or restricts or prevents the oscillations in the system. What is damping? It tries to reduce the oscillation, or it is tries to decrease the oscillation, or it will try to prevent the oscillations in the oscillations of the transient response. So system can be classified as four depending on the damping effect. We know overdamped systems, that is transients in the system exponentially decays to steady state without any oscillations. What is overdamped system? It transients in the transient response in the system exponentially decays to steady state without any oscillations. Critically damped system, so I told critically damped means when the zeta is equal to 1. So that is transients in the system decay to steady state without any oscillations in shortest possible time. So when zeta is between 0 and 1, it is called as underdamped system. So that is underdamped system means system transients oscillates with the amplitude of oscillation gradually decreasing to 0. And the undamped system when zeta is equal to 0, then it is called as undamped systems. That means system keeps on oscillating at its natural frequency without any decay in amplitude. So here it is there will be amplifications or transient response will be there. It won't change, it won't decrease, it is keep on oscillating. So that is shown here the response. So here type of damping. So this yellow waveform, the waveform shown by color yellow is the underdamped one. So oscillations will be there and finally it will go to steady state. Just observe. And the next one is critically damped means there is no oscillations actually. Linearly it will increase and directly it will go to steady state. And undamped system means it is marked by red color, red color waveform, that is when z is equal to 0 it is undamped, it is called as undamped system. And there will be there is no steady state actually, there is a oscillation. This oscillation will be there till infinity and there is no decrement in the oscillations. And another one is overdamped one. So there is no like it is directly going to steady state, actually it is linearly increasing. So this is about different type of uh, second order systems based on the value of zeta. So next we'll see the roots of this second order system and derivations. Thank you.